it's at the pole, and then tomorrow we're actually going to graph this. And it's just kind of time consuming, so that's why I want to hold it for that. So polar is beautiful. Okay, here's a polar graph. Yeah, they're so pretty. So I could actually do, let's do 1 minus 5 sine. Okay, here's like a polar graph. But, oops, right, here's a polar graph. So if you notice, polar is sweeping out as it's being graphed. What direction is it going? Counterclockwise. So it's moving counterclockwise, and it's moving in this circular rotation as you're going. So polar, as we go and plot these, now we're going to have this point here, that is going to be the r theta. So that's a polar coordinate. And it's always seems so backwards because you have to plug in the theta to get the r. So you'd think it'd be theta r, but it's r theta. Okay? And so basically r is how far out you go, and theta is the distance, like the angle that you're facing. So for instance, if I was facing pi over 4, I'm going to go and face pi over 4, and then let's say that I wanted to go 4 root 2. Then as I face pi over 4, I go out 1 root 2, 2 root 2, 3 root 2, 4 root 2, and then that's where I plot the point. Does that make sense? So let's say that I was facing pi. Then now I face pi, and then let's say that my r was 2. So I face pi, and then I go out 1, 2. So that would be that point. So it's in this sweeping, pretty way that you're like thinking of just going counterclockwise. Now, I need you all to stand up for a second. Okay? We're going to stand up. And this is going to be 0. So this way, face this way, and this is theta equals 0. Now, turn 90 degrees to your left, counterclockwise. And which way are we facing now? Pi over 2. Turn another 90 degrees, and now we are facing pi. Pi. Turn another 90 degrees, and now we are facing 3 pi over 2. Turn another 90, and we are at 2 pi. Okay, so let's start here, and let's say that I want to do the point pi 3. So the first thing we're going to do is we're going to sweep to face pi, and then we're going to go out a directed distance of 3. 1, 2, 3.
Big steps.
Okay. So it says it's my polar. This is my polar. Where are you in rectangular right now?
3, 0.
So think about it, because this is your x-axis, this is your y-axis, right? Where did you just go? You went to -3, 0. Okay, now I want you to find, let's see, I want you to go 2 pi and go -3. So sweep to 2 pi. Whew. So I'm at 2 pi, and then I go -3. Oh, back to 3. What point are you at? The same spot. So again, this one is at -3, 0. Crazy. Okay, let's say pi over 2, 2. Pi over 2, 2. Don't say it aloud. Think in your head where you're at. Peyton, where are you? What rectangular point? Huh? What? So this is our polar point. So we face pi over 2, and then we went a directed distance of 2. What rectangular point are you at right now? Close. 0, 2. So that would be the rectangular point. Okay, have a seat. So my question to you, are polar points unique? Like if I was at this spot right here, is there only one way to get to it?
No.
How many ways are there?
Infinite.
Infinite. I could face pi and go out 2. I could face 3 pi and go out 2. I could face 5 pi and go out 2. Etc., 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 right? Or I could face 0 and go back 2. I could face 2 pi and go back 2. So how many places? Like, there's an infinite amount. Are rectangular points unique?
Yes.
Yeah. 3, 2. Any other way to get to 3, 2? No. Okay? So polar points are going to be unique, but rectangular points are unique, polar or not. And that's what this is kind of telling me right here. Okay, on this guy, you're going to want to highlight this, this, and this. So all of these guys, and I'm going to go ahead and just put this into theta instead of five. Okay, so here, if I did SOHCAHTOA with this angle, so if I went out some r, and this is my angle, and I did all my SOHCAHTOA, I could see where these guys came from. Yes? So if I solve now for the x here, I get out the equation I want. If I solve for this y, I get out the equation that I want. These guys right here, we will use a ton. Okay? Where is this formula coming from in the right triangle? Pythagorean theorem. Okay? So all of this is coming from this right triangle relationship. Now, when we do our unit circle and different things, and we even look at our hands, xy goes what for trig? X goes with what? The cosine. Y goes with
Sine.
Oh, look here. X goes with cosine. Y goes with sine. Okay, it's just always, they go hand in hand. They're best buddies. They're like Grant and Guar. Okay. So, let's look at this. Again, this would be pre-calc right now. And then we'll get into some calc, okay? But it says, find the polar equation for the circle and support graphically. Well, let's just first look at the rectangular. Where am I centered from this rectangular equation right here? So I'm centered at 0, 3. And what's my radius? 3. So my circle would look at 1, 2, 3. There's my centered one. So I went out 3, 3, 3, 3. Do you agree that's what my circle would look like? That is like the best circle I've ever drawn by hand. I'm not even kidding.
Take a picture of it.
Gosh, I can never draw good circles. Okay. Now let's look if I went into polar. So let's FOIL that y minus 3 squared. Can you guys all FOIL that? What happens to those 9s? Well, that was 9. They went away. What does x squared plus y squared equal?
R squared.
R squared. Minus 6 equal
R sine theta.
So now I'm down to this equation. Agreed? What's wrong, Kellen? Ask me. Ask me. So I used what y equals. So remember back here? Well, why do I do this? Okay, but remember right here? That's what I used. Okay, so now what I'm going to go ahead and do is I'm going to factor out an r. And then I'm going to use my zero product property. Remember when two things multiplied equals 0, we can set them each equal to 0. Solve for r here, and this is what I get. So r equals 0 is nothing. That's just at the pole. We're not doing anything. So we're going to ignore that, and we're going to go look at this one right here. So let's get out our graphing calculators. And let's go plug in. Oh, sorry, first change your mode to polar. Helen, you have one? Okay, so change your mode to polar, and then let's put this in 6 sine theta. Now theta is the default button when I hit that X right there. Well, hold on, let's go graph. And we're in like 10 by 10, and this is a rectangle, so you can, if you want, you can zoom square, and it will make it so that you can see. Okay, that basically those tick marks will be equivalent now. Okay, so that is a circle. Okay. So now what if I went second calc and I want to pick some values. And let's start at 0 for my theta. So here at 0, I'm right there. And think about if I plugged in 0, what's sine of 0? 0. So when I face 0, I'm at 0. Now I'm going to do pi divided by 4. What will I get when I put in pi divided by 4 here?
Radical 2 over 2.
Radical 2 over 2 times 6, which would be 3 radical 2, which should put me at the point 3, 3. So think about that relationship. If I have this 3 radical 2 distance that I'm going out, yes, remember in geometry that'd be 3, 3, 3 radical 2, x, x, x radical 2. Okay, so that pi over 4 is making the, oh my gosh, what's that called? Isosceles. Okay, the 60, 60, 30, 60.
45.
No, 45, 45, 90. Oh my gosh, I couldn't do it. Thank you. I was like, why is my brain stopped? Okay, the 45, 45, 90. So when I have my 45, 45, 90, that's what's happening at that pi over 4. So I know, I know that this guy right here is making that angle for 45. Okay, so what if I did pi over 2? So now I face the pi over 2, and I go up to 6. And let's see if I plugged in pi over 2 here. Sine of pi over 2 is 1. Directed distance times 6 would be now 6. Okay? Okay, so do they match up? Yes. So let's say that I wanted to convert this coordinate to a rectangular coordinate. There's two ways we could do that. We could do it graphically. Oh. Or we could do it with our equations. Now, equations would be like when it's not when it's basically going to be on, what are those quadrantals? If it's on a quadrantal, then graphically is easier. If it's not, if it's like at pi over 6 or pi over 5, then we're going to want to go to the equations. Okay, so graphically, we're going to think we face the pi, so I'm facing pi, and then I go out how many? So what point is that rectangularly? -2, 0. So that's the rectangular coordinate for that polar coordinate. If I did my equations, then I have to go to where x equals r cosine theta and y equals r sine theta. And then I plug in my r and my cosine. Or sorry, my r and my theta. I go plug those values in to cosine and sine. So here x equals 2 times the cosine of pi, which would end up being -1 times 2 is -2. Y, when I go plug those in, 2 times the sine now of pi, which gives me 0. So do I get the same thing? Yes. And sometimes graphically is going to be way too hard to do, and we have to go back to the equations. And those equations, you guys, you're going to use a ton. Yes.
These are only the equations I can ever the axis.
Yeah. Aren't those called quadrantals?
Sure.
Okay. Okay. So I was trying to remember that. Okay. But yes. Okay, so slope. And here's where I'm going to heed this warning. Warning. Okay? So you get a big fatty warning here. Because I would say a third or more students, even when I yell this out, it's the warning and the flashing lights, there will at least in here be 2 of you. That's my prediction. I hope it's 0. But that will do, oh, slope of a polar, I'm going to do r prime. No! Okay? R prime is not slope. We're going to learn what that is in 9.5. But R prime is not slope. Okay? And so many people want to do it. And it seems like so easy. All I do is take R prime and I plug in that whole point. I'm good. No. Okay? This takes so much more work. Basically, you're going to have to go and use these 2 equations. So you start with these equations. Bless you.
Thank you.
And you plug in your R. Then you have parametric equations. Then the rest of this now is just parametric. So you find your x prime and y prime and do your dy over your dx. This part right here, this is the biggie. So you have to get you have to get your set of parametric equations first. Okay? So when we are talking about slope and polar, is it r prime?
No.
No! Even though it seems so nice and easy. And then really quick before we go do one, horizontal and vertical tangents are now going to be the same. Okay? Just like parametric. get those equations from x and y that I told you we're going to use a ton of, and this is just the same as parametric. Okay, so let's go do this example. What is the slope of the tangent line to the polar curve at the point where theta equals 0? And this is the big no. This is the no part, so don't write it down. This is what everybody wants to do. Oh, r prime is negative 2 sine theta. R prime evaluated at pi is going to be negative 2 times sine of 0, which is 0. And I'm going to pick B. And guess what?
Wait, it's not sine of 0, it's sine of
Oh, of pi. Sorry. Same thing. And so I'm going to pick B. Yes?
-1.
And this is all wrong. But see how easy this was for me to do? And so it's so tempting. But this is bad. This is a no-no. This is not finding slope. Okay? So to find the slope, the first thing we have to do is get our two new equations. So in ours, that one was a good one. Okay, in ours, we're going to plug in the 2 cosine theta minus 1 for r. That's our r that we plug in. R's. Jackson even told me to stop. Oh, my heart is broke, Jackson.
That's so rude.
Jackson. Alright, so those are the two equations that I've now created. So now it's just parametric. They're usually pretty gross though. So for parametric, to find the slope, I have to take dy over dx. That's what we're going to do. I know, right? Oops, not a t. Theta here. So let's go find x prime. Zach, really, do you need water? Okay. So I'm going to do product rule. First times the derivative of the second plus the second times the derivative of the first. Yes. You could FOIL first if you wanted to. Okay? Either way, the answer will be the same. I don't care how you guys like to simplify it or whatnot. You can leave it all in one big lump without simplifying. So I just kind of did stuff that helped me. So then I'm going to find my dy dx by taking the derivative of the y over the derivative of the x. And again, however you simplified it, as long as it's correct, it's fine. Or if you didn't simplify it, that's fine too. Is everybody okay to here? now all we have to do is, it wants me to find the slope when theta is pi. So can I put equals and just plug in pi? Josiah? No? How are you going to do this? Are you just gonna go underneath with no equals and plug in pi? That'd be fine. You could, as long, if you just don't use equals and go underneath and just plug in pi. Or I could say that dy dx evaluated at pi equals, if we want to get good notation. So let's see. -1, -2, -1, -0 over -0. 3, -3 over 0, thank you. Which would be undefined. To be a vertical tangent going on there. Because the dy was not 0, right? I'd have 0 over 0 if the dy was. What do you think? Okay, skip the next one and go to the one after that with slope again. It's another multiple choice down there. Try that with your buddies, and then we'll come back up to the other one. So see if you can do the next slope one. Who? You. Sorry, no. How much easier would it have been if R being a slope? I know. So when you're doing it, that's what you should think. You should be like, oh, this is too easy. This can't be right. Oh, it's not right. Why?
You said it at the same time.
Okay. Excuse me. The derivative. What would that be? Cosine theta times 2 cosine theta. So you take the derivative as well. First, the second plus the second. Oh, right here, yes, thank you. Got it.
Put your dx on top.
Okay, I'm good. I'm good. Huh?
It'd be negative 2 times 0 plus 2 times because theta equals 0.
Okay, good now?
Yep.
Okay. So, what kind of tangent's going on here? Yeah, there's a horizontal tangent at 0.
Never mind.
Everybody good? So now let's go back up to this one. And it wants me to find the polar points of horizontal tangency for this r equals a sine theta. So if I want to find where I'm going to be a horizontal tangent, I'm looking for what? dy d
Theta.
theta equals 0. Is that all?
No, dx d theta doesn't.
Okay, and dx d theta doesn't equal 0. So do I basically have to go find everything again?
Yep.
Yeah. Not just a short little thing to do. So this is pretty extensive. So I need to go find dy d theta and dx d theta. Before I can find dy d theta, I have to find out what y is. Before I can find dx d theta, I have to find out what x is. I told you you're going to use these equations all the time. So start with your x and y, take your derivatives, and then you're going to set the derivatives equal to 0. A is just a constant. It's just showing that it doesn't really matter what the A is here. Yeah. So let's see if we get the same derivatives. Everybody good with the derivatives? Raise your hand if you want more time for the derivatives. So now I know that I need to find where does my dy d theta equal 0. So that's going to happen when theta equals what? What can I plug into this one?
2.
0, then what?
It says pi is not included.
Good. So I go 0, and then pi is the next one, and then 2 pi, and I could have went back to negative pi, but they told me I'm only looking from 0 inclusively to pi exclusively. So 0 is the only one from this part. What about over here? What makes that 0? Pi over 2. Anything else in the interval? Okay, so these are the guys I'm thinking, as long as, right? As long as my dx d theta doesn't equal 0. So what values would give me 0 on dx d theta? Ooh, that one's harder. Yeah? So it's where, let's see, a sine squared theta plus a cosine squared theta would equal 0, or a sine squared theta would equal cosine squared theta. A's could cancel. We'll go ahead and cancel them. So where does sine squared equal cosine squared? Pi over 4, but then it's also squared, so what's the other one? 3 pi over 4, and that's still in the interval. Any more in that interval? Should you keep going? Nope. So if I check now, are we good? So now I want to, so these are good. These make me happy. So now I want to, in part A, find the polar points. So remember, polar goes r theta. So where am I going to get that r from?
Plugging it in the theta.
Yeah. So we're going to plug in the theta to find that r. So what's the first theta that I plug in? 0. And what do I get out when I plug it in? 0. What's the other theta that I'm plugging in? Pi over 2. Plug it into that equation, and what do I get out? A. So that's my answer for part A. Part B now says to find them in rectangular. So rectangular is now x, y. And you have a couple options. You could go plug in the thetas up here to your x, y, or you could try to convert those graphically. Either way, you're going to get the same thing. So let's go plug in my theta into the x up above and see what happens. So plug in, what was the first one? 0? Oh, well, that's easy. What does that give me? 0. And plug in the 0 into here, and what do I get?
0.
0. Same, kind of the same. So now let's go plug in my pi over 2. So when I plug in my pi over 2 here, what do I get out?
0.
0. And when I plug in my pi over 2 here, what do I get?
A.
1 times a, which is a. And could we see that graphically how this one is the same? Face your pi over 2, right? So face the pi over 2 and go out to a. And we are at 0a. So we could have seen that graphically as well. Good? So you understand the difference between polar and rectangular. So then we have one more thing that we're going to do, and that's tangents at the pole. So I know they have f of a equals 0, but really it's where r is 0 and r prime is not 0. This is a tangent at the pole. And I'm going to show you what that means. But first we're going to find them. Tangents at the pole are going to help you to graph. So if I want to find the tangents at the pole of this polar equation, I'm going to say where r equals 0. So let's go find where r would be 0 is where 5 theta would equal, what would be the first thing in there? 0. So if I solve, that would be where theta divided by 5 would be 0. What's the next one? Pi divided by 5, and I am at pi over 5. What's the next one? 2 pi, so now I'm at 2 pi over 5. So these are all still unique. 3 pi would be the next one. So 3 pi over 5. 4 pi would be the next one. So 4 pi over 5. And then 5 pi would be the next one, which is actually going to be pi. And pi and 0 are the same line, if I'm thinking of a line. So if I face 0 and pi, it's the same line. So these guys start to not be unique anymore. So these are tangents at the pole as long as r prime doesn't equal 0 there. So what's r prime? Take that derivative. -5 cosine. And plug these guys in. And say, does that equal 0? Huh? Oh yeah, I did, thank you. So if I plug those in, do I get out 0? No. So all of these guys, all are okay. So all of these are tangents at the pole. So what does that mean, right? And then before I go on, Grant, what's your question? Oh, because pi and 0 are the same line.
So why did you take our five?
Because if r prime is also 0, then it's not going to end up being a tangent at the pole. Because, again, with r prime, we're going to talk about how fast it's changing from the pole. And that's like, it's not changing there. And we'll get into that in line 5. Okay? Okay, so let's sketch our xy axes. And it's harder. When we go to graph, I have it set up in circular for you. So I want to graph as asymptotes all those tangents at the pole. All okay. All are tangents at the pole. Like we checked them, and none of these guys equals 0. So I'm going to sketch, the tangents at the pole are going to kind of look like asymptotes in a sense. So here, this guy right here is my theta equals 0. And you see how that's also theta equals pi? So that's why we exclude it. It's just repetitive. Then I want to go to 5 pi. So theta equals...
Pi over 5.
That's what I meant to say. Gosh, it's a Wednesday, Chris. Give me some slack. Okay.
You only get slack on Mondays and Fridays.
Oh, okay. Hardcore. Yeah. Alright, and then we go to 2 pi over 5. And then we go to 3 pi over 5. And then we go to 4 pi over 5. Huh? I know. It's kind of fun. Okay, so this is fun. This helps me. And we're going to graph a lot more of these, but for now I'm going to show you what the shape ends up being. And since, was this a sine or a cosine to begin with? Sine. Sine goes with what? X or y? Y. So this is going to be symmetric about the y-axis. Okay? So as I graph this, I know since it was a sine, it's symmetrical about the y. But the way that this guy looks It is. It's a flower. It's a rose.
It's not a rose.
That's what they're
It's like a different rose. Oh. It's a different rose. That's what.
because that's the way it's going to be graphed, and we're going to get into that tomorrow. We're going to graph a lot more, okay? And you can look ahead in your notes. So these tangents at the pole basically let me know that in between them, it's kind of symmetrical going on, okay? And the sign lets me know that if I fold it over the y, that they touch as well. But that's what the tangents of the pole are going to help me to do, and we're going to do this more tomorrow. Okay? Okay, you can answer now your essential questions 1 through, how many are there? Yeah, 1 through 4.